Hello everyone. In this video, we are discussing electric dipole. What is an electric dipole? Look at the board. We have two charges. So this is Q and this one is minus Q. So look at this. There are two charges separated by a distance. These two charges are equal in magnitude. Both of them are Q, but one is positive and negative, and they are separated by a small distance. And anyway, this setup is called an electric dipole. It is defined as an arrangement of an equal and opposite charges separated by a small distance. So look at this diagram. So this distance, this is called the dipole axis. Here, this point O, this is the center of the dipole, and the distance of one charge from the center is, we consider it as A, small letter A. Similarly, the negative charge is also A, or we can say the distance between both the charges is 2A. Next, dipole moment. Dipole moment of an electric dipole means it gives the strength of the dipole. Mathematically, it is denoted by a letter P, vector P. So we can write it mathematically, dipole moment P is equal to either of the charge, either plus Q or minus Q, only the magnitude, into the distance between them, that is 2A. So we can define dipole moment. It's a product of either the charge and the distance between them. It is a vector quantity. It has a direction. Its direction is from negative point charge to the positive along the dipole axis. So the direction is this. The direction of dipole moment is this. It is from negative to the positive point charge. Its SI unit is, look at this, SI unit, charge into distance, so that is coulomb meter. Next is electric field around an electric dipole. Look at the diagram. First one, electric field along the axial line of an electric dipole. Look at the board. We have a dipole, minus Q plus Q, separated by a small distance between, that is A plus A. And O is the center of the dipole. Now we are going to calculate the electric field along the axial line. Axial line means, so this is the dipole axis. If you extend, this is the axial line. So you're going to calculate now electric field at a point P, which I'm going to place. I can place either this side or on the other side, but anyway, let me consider here. This is a point P. It is at a distance R from the center of the dipole. Now what is the net electric field at point P? So it is clear that at point P there will be an electric field due to both plus Q and minus Q. What is the direction of electric field from a positive point charge? We have studied positive point charge, the electric field start from the charge and it directed towards infinity. So the positive charge, it has an electric field directed towards infinity. So at this point P, it will be directed towards infinity. So this is the direction of electric field due to positive charge. So I am writing it is E plus. In the same way, for a negative point charge, the electric field, it's directed from infinity to the point charge. So at this point P, due to minus Q, there is an electric field, negative electric field. What will be its direction? It's directed from infinity to the charge. So at this point P, it will be directed from point P to the point charge. So I'm marking it this. So this is E minus. Okay. Now, the net electric field will be the vector sum of these two. Look at the diagram. Which field will be stronger, whether this E plus or E minus? See this. The positive electric field will be stronger because we have studied the electric field at a point is inversely proportional to the distance. Inversely proportional to the square of the distance. Clear? So look at this diagram. What is the distance between plus Q and P? Plus Q and P. That distance is from here, this distance. See, from center to P it is R, and from center to Q plus Q it is A. So this distance will be R minus A. In the same way, what will be the distance between minus Q and P? From P to center it is R, and from center to minus Q it is A. So the distance it is R plus A. So look at this. R minus A is the distance of plus Q from P. And R plus A, it is the distance between minus Q and P. Obviously, R plus A is greater than R minus A. So that means point P is much far from minus Q than plus Q. So, and we know that the electric field is inversely proportional to the square of the distance between them. So it's clear that the E plus, in this case, E plus is greater than E minus. So in this particular case, you can say that this E plus is greater than E minus. Anyway, the vector sum of these two, E plus and E minus, will give you the net electric field at this point P. The electric field at a point, due to a point charge, we have already studied it is E is equal to KQ divided by R square, where K is equal to 1 by 4 pi epsilon naught. Now, what will be the electric field at point P due to the plus Q, that is E plus? E plus is equal to, that is KQ plus Q divided by square of the distance. Now, what is the distance between plus Q and P? It is R minus A. So you can write down it is R minus A whole square. Similarly, what will be E minus? This E minus is equal to minus KQ divided by, what is the distance between minus Q and P? It is R plus A. So it is R plus A whole square. Now, the net electric field. Net electric field is equal to the sum of E plus and E minus. Let us substitute these two values here. So you will get it is KQ divided by R minus A whole square plus minus KQ divided by R plus A whole square. Now let's take the common outside. KQ It's a common factor. So I'm taking this outside, so I can write it as KQ. So I'm taking KQ outside, I can write it as 1 by R minus A whole square minus 1 by R plus A whole square. The net electric field along the axial line E is equal to, so I'm writing, it's an electric field along the axial line, so it is EX. This AX stands for axial line, is equal to KQ into this. So inside the bracket, we are going to expand it. Let's take the LCM. So it will be KQ, you can say it is R plus A whole square minus R minus A whole square, all divided by the LCM is R minus A whole square into R plus A whole square. So let's take the LCM. It is look at this, R minus A into R plus A. So you can say that is R square minus A square. Again, R minus A into R plus A. Again, that is R square minus A square is equal to. Look at this. I'm going to rearrange this formula, that is KQ into, it's 4A, so I'm writing it is 2 into AR divided by, this is R square minus A square into R square minus A square, so that is R square minus A square whole square. Look at this, Q into 2A. So we know that dipole moment P is equal to Q into 2A. So what is left? That is the net electric field EX is equal to 2K PR divided by R square minus A square whole square. Look at this. This equation will give you the net electric field at point P. Now the special case. Look at this. If you are considering the point P, which is at a very large distance from the dipole, that means very large means not at infinity, it means the value of R, it is very greater than A. What is A? Half distance between the dipole. The distance between the dipole is 2A and half of the distance is it's A. So if you consider the point P is far, that means R, if R is very greater than A, so in this equation you can neglect the value of A. You can neglect this value A. So if you neglect this, so you know what will happen here. So here this A square you are neglecting. So once you neglect it, r square whole square. So it will become r raised to 4, or r and 4 is cut, it will be r cube. So you can write down, in this special case, Ex is equal to 2kp divided by r cube. It's clear that the net electric field is inversely proportional to the cube of the distance. Cube of the distance. What is this distance? Distance of the point P and between point P and the center of the dipole. Now we have calculated the net electric field Ex. What will be the direction of this net electric field? Come to this point P. Look at this. One is E plus and the other one is E minus. So in this case, it's clear that the net electric field will be along the direction of the strongest. Which one is the strongest? It's clear that when you compare these two electric fields, E minus and E plus, it's clear that E plus is stronger than E minus. So obviously the net electric field will be along the direction of the stronger one. So that is Ex, the net electric field will be along the direction of this one. That is, it is directed along the axial line but towards the infinity. Okay, now what about dipole moment? What is the direction of dipole moment? We know it is directed from negative point charge to the positive along the axial line. Along the axial line. So what will be the direction of dipole moment? It is also negative to positive. Now look at these two. So what is our conclusion? We can say that along the axial line, the direction, that means the direction of the net electric field and the dipole moment, they will be parallel. So you can say Ex is parallel to dipole moment. If the point P you're considering in the left hand side, so let's consider the point P. So let it be, this is the axial line. So let's consider point P is here, and again the point P is at a distance r from the center of the dipole. Now at point P there will be electric field due to both minus q and plus q. Okay, so what will be the direction of electric field due to plus q? So positive charge, it is directed towards infinity. So at point P, this will be the direction of electric field due to minus charge. So this is E minus. Sorry, E plus, positive electric field. What about the electric field due to minus q? It is directed from infinity towards the charge. So here is the charge from infinity to the charge. So it is the direction of E minus. Now in this case, at this point P, which field will be stronger than the other? Whether it is E plus or E minus. See, which charge is closer to the point P? In this case, minus q is close to the point P than plus q. So we can write down, that is, the electric field due to minus charge, minus q, is stronger than the electric field due to the positive charge E plus. And we know the net electric field will be along the direction of the strongest. So in this case, look at this. What is the direction of the strongest one? And this is this E minus. So here the direction of E axial is from infinity to the charge. So it is the direction of Ex. Okay. Similarly, what about the direction of dipole moment? Dipole moment is from negative to P. So in this case, the direction of dipole moment P is directed from negative to P. So Now look at this, the direction of net electric field and the dipole moment. So here it's clear that the net electric field E axial is, again, it is parallel to the dipole moment P. So that we can conclude, anywhere you take the point P, whether it is on the right hand side or in the left hand side or anywhere, the net electric field Ex will be always parallel to the dipole moment P. Next is electric field at any point along the equatorial line of a dipole. So look at this. So here we have a dipole. O is the center of the dipole. Now the equatorial line. The equatorial line means any line which is passing through the center of the dipole and it is perpendicular to the dipole axis. So this is an equatorial line. Okay. Now let us consider a point on this equatorial line. So let it be here. So this is point P. Okay. The distance of the point P from the center of the dipole is R. And let me complete this triangle. This is a triangle. Now it is clear that, look at this triangle. Both the triangles, they both are a right-angled triangle. Now what will be this distance? It will be the hypotenuse. So the distance hypotenuse. So you can see the base is A and the height is R. So the hypotenuse will be, according to the Pythagoras theorem, you can write it is under root A square plus R square. So I am writing it is R square plus A square under root, or also you can write down it's all raised to 1 by 2. What about this triangle? Here also the base is A and perpendicular is R, then the hypotenuse will be the same way. I can write it is R square plus A square and it is under root, so all raised to 1 by 2. Now at this point P, there will be an electric field due to both minus Q and plus Q, and the vector sum will give you the net electric field. Okay, so now let's consider the electric field due to plus Q. You know, it's a positive point charge. So the electric field will be directed from the charge towards infinity. So the electric field will be along this direction. So I can say, so this will be the direction of E plus. Okay. In the same way, what will be the direction of E minus? E minus means electric field due to minus Q. It will be directed from infinity to the charge. So infinity to the charge. So at this point P, the direction of E minus will be this. So this is the direction of E minus. Okay. Now, both electric field, okay, they are not along the same line. Clear? So they are at two different angles. Now let us consider this triangle. So you not need to, it is understood that this triangle is an isosceles triangle, because you can see here that means both sides of this bigger triangle is the same. It is R square plus A square all raised to 1 by 2. Here also is the same value. So isosceles triangle, you know, this angle is theta. This will also be theta, because base angles are equal in an isosceles triangle. Okay. Now, what I am going to do, electric field, it is a vector quantity. So both E plus and E minus, we are going to resolve both of them into their rectangular components. Means their cos component and sine component. Look at the board carefully. So let's consider a line which is parallel to this one, and this is perpendicular to the dipole. Now, look at this theta. Look at that line. You can say this angle is also theta. Why? Because look at this. The dipole length, the axis of the dipole, and this line, they are parallel, and this line will act as a transverse. So these two angles are the corresponding angles. So corresponding angles are equal. Now I am going to resolve this E plus into its rectangular components. So one component will be along this, okay, and that will be E plus sine theta, means sine component, and the other component will be along this, and it will be E plus cos theta. Okay, that means I have resolved E plus into its rectangular components. One is sine component and the other one is cos component. So is that clear? Yes. In the same way, I'm going to resolve E minus also. Look at this. The axis of a dipole. Again, a line parallel to the dipole axis. This angle is theta, and see this line, it can be act as a transverse. So this angle will also be the same angle theta, because these two angles are the opposite interior angles. Okay, in a transverse. Again, this E minus I am going to resolve into its rectangular components. One is along this will be E minus sine theta, that means sine component, and the other one will be along this direction. So what is this? This is E minus cos theta. See, remember this E minus into cos theta. It is not E minus cos theta. So all these are, this plus or minus, it indicates what? The electric field of the positive charge or the electric field of the negative charge. So now you have resolved both E plus and E minus into their rectangular components. Now this is very important. Look at this. The electric field at point P, due to minus Q and plus Q, the directions are different. Okay, but the magnitudes are same. Why? Because the distance from the point charge to the point P is this, and for the positive charge also, the distance between positive charge and point P is also the same. So that means the magnitude wise, the magnitude of both the electric field at point P is the same, but their directions are different. And now look at this. This E plus sine theta, E plus into sine theta, and E minus into sine theta, they are actually equal. Clear? So you can say that, see, this E plus sine theta, its magnitude is equal to the magnitude of E minus into sine theta, and they are in the opposite direction, and obviously they both will cancel each other. So it's clear that along the equatorial line, upwards or downward, the electric field is zero. Okay. Hence, the electric field E plus sine theta, E minus sine theta. That means the sine component of both E plus and E minus can be cancelled. So at present, it's not there. It's cancelled. This is point P, and this electric field is also cancelled. Okay, now look at this. The electric field along the equatorial line, it's perpendicular equatorial line, that is E plus cos theta and E minus cos theta. Magnitude wise they are equal, and the directions are also equal. So obviously these two will not get cancel each other, but they both will get added up. Okay, so the magnitude of this E plus cos theta is equal to, it is E minus cos theta. So I can simply write down this is equal to E cos theta, either for both plus or minus, doesn't matter, because both of them, E plus cos theta and E minus cos theta, E minus into cos theta, they are the same, they have the same values. Okay, and they are along the same direction, and they will get added up. So what will be the net electric field at this point P? The net electric field will be, I am writing it as E equatorial. This EQ stands for the equatorial line. Electric field along at any point on the equatorial line. That is E equatorial is the sum of both. The sum of both. So I can write down that is E plus into cos theta plus E minus into cos theta. So anyway, their values are the same. That is E cos theta plus E cos theta. Or finally, I can write down E equatorial is equal to 2E cos theta. So this is equation number 1. Got it? The electric field at a point P due to the point charge, either plus Q or minus Q. We have the general formula, that is E is equal to, it is KQ divided by R square. This is the general equation for an electric field at a point due to a point charge. Now what will be for this plus Q? What will be this E plus? E plus will be is equal to, it will be KQ divided by distance. What is the distance? It is under root R square plus A square. So, and here you have to write down the square of the distance. So obviously the under root will get cancelled. So that is, it's like this, it is R square plus A square under root whole square. So what will happen? The square and the under root will get cancelled and you will get, it is only R square plus A square. Clear? Even for E minus also you will get the same value, that is K, it's minus KQ divided by R square plus A square. Clear? The distance is same. And we know, we have already seen this E plus, the magnitude of this E plus and E minus, they are equal. So let's consider it is E, this E. So what is the value of this E? You can say that this value of E will be is equal to, see, I am not going to consider the direction. Okay, I am not going to consider direction, only the magnitude. So that will be KQ, no need to put plus or minus, KQ divided by R square plus A square. Equation number 2. Look at this diagram. The same diagram. See this triangle. It's a right angular triangle and this is theta. What is cos theta? Cos theta is equal to the adjacent side divided by hypotenuse. For this theta, what is the adjacent side? Adjacent side is the distance between the center of the dipole and minus Q. What is this? It's A. A divided by hypotenuse. What is the hypotenuse? The distance between minus Q and the point P. What it is? It is under root R square plus A square. So it is R square plus A square under root. Equation number 3. Okay. Now we are going to substitute equation number 2 and 3 in equation number 1. So that is, you are substituting equation number 2 and equation number 3 in equation number 1. What is equation number 1? That is the net electric field E equatorial is equal to, it is 2E cos theta. So this was equation number 1. So that is, you can write down 2 into, what is E? E, it's given, it is written in the equation number 2 that it is KQ divided by R square plus A square into, what is cos theta? Cos theta is given in equation number 3, that is A divided by R square plus A square all raised to 1 by 2. Now look at this. 2QA. We know dipole moment P, small letter p, dipole moment. P is equal to, it is 2QA. So that you can write down the net electric field at point P, E equatorial, is equal to KP divided by look at this, R square plus A square all raised to 1. This is R square plus A square all raised to 1 by 2. So you are multiplying. So when you are multiplying, you have to, the same value you are multiplying. That means the power you have to add. So it is 1 plus, so you can write down it is R square plus A square all raised to 1 plus 1 by 2. So that is 3 by 2. So you will get this equation. That is E equatorial is equal to Kp divided by R square plus A square all raised to, the whole raised to 3 by 2. This equation will give you the net electric field at point P. Now the special case. Special case means when the point P is placed at a large distance from the center of the dipole. If it is a large distance, that means it's a special case. We can say that the value of R small r is very greater than A. So if R is very greater than A, you can neglect the value of A in the above equation. So look at the board. You are neglecting A or A square, you are neglected. Now what is left? It become R square all raised to 3 by 2. And this 2 and 2 will be cut, and finally you will get it is R cube. So in this special case, the net electric field E equatorial is equal to Kp divided by R cube. And here it is clear that this electric field along the equatorial line is inversely proportional to the cube of the distance. Okay. Now, the direction of electric field at any point on the equatorial line. Okay, so we have derived the formula of equatorial, the electric field along the equatorial line, that is E equatorial is equal to Kp divided by R cube. Clear? And when you analyze the diagram, you will understand the direction of this electric field is along this. This is the net electric field direction, E equatorial. Because it's clear that there are two electric field at this point P due to plus Q and minus Q. And when we resolve them, the sine components get cancelled and cos components get added. And then final electric field will be along this direction. Now, what will be the direction of dipole moment? We know it is from negative to the positive. So negative to the positive. So here the dipole moment P, its direction is from negative to the point, negative to the positive. Now see both of them. It is clear that equatorial and dipole moment P, they are anti-parallel. Not only any point anywhere above the dipole, even you consider any point below the dipole also, remember the net electric field and the dipole moment, they both will be always anti-parallel. So hence you can conclude this A equatorial is always anti-parallel to the dipole moment P. Okay.